Good day, grade 12 chemistry students. So today we're learning about electron configurations in the periodic table. That's what all this means here. The periodic table is divided into something called SPD blocks and F blocks on the periodic table. We're going to talk about what that means, explain what electron configuration means, explain what shells and subshells mean, and what you've done previously is this one right here. You already know through experimental observations how Ernest Rutherford and Niels Bohr contributes to the planetary model of the hydrogen atom. We are just going to quickly review what Bohr said. He said electrons do not radiate energy as they orbit the nucleus. They have constant energy in orbit. They're in shells. That's a key word there. And another thing that he said is that they can change their energy level by undergoing a transition from one stationary state to another. This is what we call a quantum leap, okay? Or a quantum leap is a good way of saying that, or quantum shift. The colors produced by spectra in the lab that you did is from electrons jumping from one shell to another. They are disapparating, if we can use a Harry Potter term. From you give it energy, it jumps up, but when it jumps back down to a lower state, it releases the energy in the form of light. And the color of light determines the size or magnitude of the jump. So we're going to get right into quantum mechanics, which is going to help us reach our learning goal today. But we have to know about Heisenberg, and Heisenberg developed the uncertainty principle. We talked about that. And what that tells us about an electron is that it's impossible to know the momentum and location of an electron at the same time. Really, what he began to think that electrons are behaving as waves. In 1923, de Broglie also took that wave idea further, and he said if light could behave like particles, so light behaves like particles, then particles such as electrons could behave like waves. And he actually came up with formulas to describe the wavelength of those waves. Schrodinger, we're going to talk about his equation today, but he developed a mathematical model that determines the energy level and wave properties of the hydrogen atom as well as other atoms. So he actually came up with equations that we're going to take a look at. Together, our modern view of atoms is that electrons don't travel in orbits. No, no, no. They travel in what we call orbitals. And orbitals are defined as regions in space where there is a probability of finding an electron. So what that means is that we can't tell where the electron is, but we can use mathematical models to predict that they exist within a three-dimensional shape. So just keep that in mind, guys, and just repeat that last comment that I just made there of what an orbital is. It's basically a mathematical model saying that the electron can exist in that area. We don't know exactly where it is. We know it is within that specified volume, which is specified by mathematics. Okay, so the postulates of quantum theory, the main ideas of quantum theory is that just like Bohr, it requires energy. Sorry, you can have a change in energy level requires absorption or emission of energy. So you give it energy, it jumps up. An energy level, when it jumps back down, it releases light. So Bohr's idea still holds true. And then we have wavelength relates to energy change. Okay, so again, this is still a Bohr idea. Now, lastly, what we say is in quantum theory, we say that energy states of particles or electrons can be described by 4 sets of principal quantum numbers. So when we talk about electrons, these quantum numbers essentially are just like you have your house has an address. Each electron has an address, okay? Each electron has an address which is defined by these quantum numbers. So that address, these principal numbers or principal quantum numbers define where that electron is. Okay, so our 4 quantum numbers, the first quantum number is the main orbits for the electrons. So these are the main energy level shells. So when we say N, what we're really talking about, this guys refers to the period on the periodic table, okay? So if I say period 1, again, how many electrons can go into period 1? Well, it has 2 elements, so it holds 1. The second period holds 8, and so on. So that first quantum number actually describes the main energy level. The second quantum number, what it describes is what we call the subshell. And it defines the shape that the actual electrons fitted in. And there's actually 4 different shapes. They're assigned a letter, S, P, D, or F. Each one has a different shape. So within that different shaped orbital, we have the third quantum number. And the third quantum number is defined as the magnetic quantum number. And this one's going to be confusing. We're not going to be able to understand this one till a little bit later, but it's due to the three-dimensional orientation of the orbits. And so that means within the orbital itself, okay, there's actually little sections within that orbital where electrons can sit, and they have various energies depending on where they are within a magnetic field. I know that's probably confusing. And finally, the fourth quantum number is what we call the spin, okay? And the spin, what it means is that electrons actually can have a spin, okay? And it's kind of confusing, but electrons like to be in pairs, okay? And when one electron has one spin in one direction, the other electron that goes with it, because electrons like to be in pairs, likes to have the opposite spin. And because they have the opposite spin, I know that's actually, because they have the opposite spin, they sort of complete each other. And that's exactly how we show it. We show an arrow up and an arrow down to representing that they have different spins and they stabilize each other. So what we're going to do is we're going to focus on that secondary quantum number. The first quantum number is, if you look at your periodic table, look at that beautiful periodic table. The first one, you have your periods, which represents the shells, but you also have the shapes, okay, which come from the second quantum number. So our second quantum number, which is represented by L, tells us the shape. So overall, when we look at an atom, what it looks like three-dimensionally is it looks like a Russian nesting doll here. Okay, we got the Beatles here, nesting dolls. I wish I actually owned this. This is pretty cool. But what it actually is you get a whole bunch of basically orbitals sitting on top of each other, so it looks like a Russian nesting doll. So before we start here, let's remember that we have four numbers to describe the address of an electron. The first one is represented by the letter N. The second one is represented by the L. And that's what we're learning so far. So the first one here is the shell that it sits in, which is almost exactly like Bohr thought about it, okay? The L is a little bit more specific. We're saying that it has a specific shape or orbital that it sits in. And finally, we'll touch on ML and MS at a little later point here. So let's focus on L right now. So the first shape that we have is what we call an s orbital. It's a spherical shape. It looks like a sphere. So if we look at it, it will actually just look like this, okay? So if you're a s orbital, basically what you are is you're an electron within that spherical shape. We don't know exactly where you are, but we know you're located somewhere within that area. So if you are in an s orbital, what we do is we actually assign you a number. We give you a number 0. So if you're in an s orbital, that means you're in the number 0, okay? If you have you could also have a principal quantum number of 2, which means you're in the second shell, and L, the second quantum number, the second part of our address says 0, so therefore you're in an s orbital. So the next type of shape that you can be is something called a p orbital, and it's the second energy level. This is when this happens, in the second energy level. And a p orbital can actually hold 8 electrons, where an s orbital can only hold 2. I didn't mention that previously. So if we use this equation to figure out how many electrons total can exist in any shell, we'll talk about this specifically tomorrow. But if we take a look at a 2p orbital, this is actually what it looks like. It's actually made up of 3 sort of orbitals, okay? So the shapes that it looks like are the following. Let's look at it. So you can be an electron that exists in any one of these dumbbells. Now each one of these dumbbell shaped things actually they can hold 2 electrons. So let's look at it again. So you can be either in, this is what we call the py orbital, the pz orbital, or the px orbital. And together, each one holds 2, so we have a total of 6 electrons that can be held in a p orbital. Now, if you're an electron in a p orbital, what you actually look like is, again, if I was going to give an electron in a p orbital a number, what I would have to say is I'd have to say n equals 2, because p orbitals, we'll find out, actually start in the second energy level. I'll give it L equals 1. So 1, actually, when we put L, actually equals a p orbital. We remember that. Now the ml, we're going to find out, can be either -1, 0, or 1. And the reason is because there's actually 3 suborbitals. So this will actually hold a maximum of 6 electrons because it's made up of 3 suborbitals. The next type of orbital that we have is represented by L equals 2, and it actually is made up of 5 orbitals, and each one of these guys can hold 2 electrons. So because of that, the maximum amount of electrons that held in a d orbital are 10 electrons. If we look at an f orbital, that's represented by the number 3. It actually can hold 14 because it's made of 7 or suborbitals. These are the 7 shapes of these suborbitals here. And all these combined together, each one holds 2, it holds 14 electrons. Now, we'll explain what this has to do with the periodic table. So let's talk about the periodic table and the orbitals that I just mentioned. So far, what I said we had was S, P, D, and F. And basically, if we look at the periodic table, this zone right here, group 1A and 2A, this is the S zone. S orbitals are actually filled within this area right here in group 1A and 2A. If we take a look further, we go to our next one. The P, this is the P block right here. All the P's are located over here. Now, all the d orbitals are located in the middle section, transition metals. And finally, the lanthanides and actinides, this is where the f orbitals fill up. Now, why do we care? Well, we can write something called electron configurations, which basically tell you, you can pick any atom and it will tell you where the electrons are and what type of orbitals they are in. For example, what I've done here is I've taken a periodic table and we've replaced, I've just put 1s here, and if we take a look, the electron configuration for helium, I actually moved helium from here over here, is actually going to be what we call 1s2. Okay? Okay, I've given you a bit of background. I think what we're going to do is we're going to talk about it in class some more because this video is going to be too long to explain it. This is one of the most complicated things that you have to understand in this course, and confusing. So to help illuminate things, what we're going to do is we're going to talk about it more in class. I hope you took notes. Hope you come prepared for class, and we'll talk about it within our period. Thanks for watching our video. Hope you've had a nice evening.